Okay, so today we're going to look at section 7.2, quadratic forms. Quadratic forms. Before we talk about what we mean by a quadratic form, let's just point out a few things that we already know that are relatively simple. Right? So for instance, if I take a vector x and I dot it with itself, so we know something about this already. What I'm going to get back from this is the length of the vector x squared. So that's something that we already know. This is something that takes a vector x and returns a real number. Right? So, but I can also write this as something else. Right? So I could write this dot product. We've seen this before as x transpose as a matrix times x as a matrix. Right? So this is x1, x2 to xn times x1, x2 to xn. Right, so this is x transpose, and this is x. If I take this as a matrix and multiply, I'm going to get x1, x1, plus x2, x2, plus all the way down to xn, xn, which is exactly what the dot product is. Right, so this is the same thing. So I can think about this dot product as x transpose times x. This gets us a number. This gets us a matrix which has only one entry in it. So we can also think about that as a number. They really are the same thing. So this here is an example of what we call a quadratic form. We take a single vector and it returns a real number. Now, in general, what we're going to do is we're going to allow another matrix to go inside here. Right, so let me write down what I mean. So definition. A quadratic form is a map. It's a function. Right, it's a function which inputs a vector and it outputs a real number, r, of the form x transpose. So we input the vector x, we're going to x transpose, we're going to multiply by some symmetric matrix, and we're going to multiply by the vector x again. So this is just like x transpose times x, but we've got some other matrix in the middle. And we'll see some physical interpretations of what's going on with that. Remember, the matrix A we can think about as a map from Rn to Rn, right? So it's a transformation. That's a linear transformation. So this is really just a change of coordinates, and we'll see how all of those things play out with examples. Right? So, but this is a quadratic form. A quadratic form is a map then that if I input the vector x, if I have a matrix A, I can think about that as outputting a real number. So for example, so suppose let's let q at x be the quadratic form given by the matrix A, which is going to be a symmetric matrix. So let's say it's 1, minus 2, 3, 3. So that's a symmetric matrix. Then let's do a couple of things. All right, so what is Q at the vector x? Let's say 1, 2. So if this is x, then Q at x is x transpose A x. X transpose is 1, 2, across instead of down. A is 1, 3, 3 minus 2, and x is 1, 2, going down. Let's keep our matrix. So what do we get when we work this out? Let's just do the last two first. So this will be 1 plus 6. So I'll have 1, 2 times 1 plus 6, which is 7. And then I'll have 3 which is -1. So by taking ax instead of just x, we still get a vector back, and now we can think about it as a dot product, or we can think about it as a matrix multiplication. So in the end here we get 1 times 7, which is 7 plus -2. It's really a matrix. It's the matrix 5, but we're really going to write this just as the number 5. If I have a matrix with a single entry, I can really just think about that as a real number. So I get a value back. I get a number back through this quadratic form. Now, so why do we call these quadratic forms B? Let's think about what Q at X looks like more generally speaking. All right, so Q at X is X transpose AX, which is, let's say that X we don't have specific information about. We think about X just as X1, X2 times 1, 3, 3 minus 2 times X1, X2. Okay. Now, what happens if I try to simplify this? We'll do it in the same order as before. If I multiply these two, I get x1 plus 3x2. I get 3x1 minus 2x2. And now when I multiply, we get x1 times the top plus x2 times the bottom, which is x1 squared plus, we have 3x1 x2, and we have another 3x1 x2, which makes 6x1 x2, and then we have minus 2x2 squared. Remember our matrix was the matrix 1, minus 2, 3, and 3. But that was our matrix A that we started with. All right, so why is this called a quadratic form? Well, it's a quadratic function, but now it's a function of two variables, x1 and x2, rather than just a function of one variable. But it's in some sense a polynomial with these two variables, x1 and x2, but it's a degree 2, right? So the max that we see is a squared. And so this is why we call it a quadratic form. And now, next, what else can we see? What do we notice here? Well, I notice something that there's a strong relationship between our matrix A that we started with and the form of the quadratic form that we get at the end. Notice that this diagonal entry 1 corresponds to the coefficient of x1 squared. This diagonal entry -2 corresponds to the minus 2 in front of x2. And where does the 6 come from? Well, it comes from the 3 and the 3 that are on the opposite diagonal. All right, so this is the cross term. This is called our cross term because it has both x1 and x2 in it. All right, so for example, if Q at X is 3x1 squared minus 8x1 x2 minus 2x2 squared, find A. What is the symmetric matrix that corresponds to this quadratic form? Well, the symmetric matrix, just as before, our diagonal entries are going to correspond to the squared terms, 3 and minus 2. The -8 has to come from a -4 and a -4 to make this symmetric. And so this is our matrix A. Now, it doesn't have to just be a 2 by 2 matrix. What if I had a quadratic form that had 3 variables in it? All right, suppose that, so if x were x1, x2, x3, so we're looking at R3 instead of just R2. Now, so a form of this form might take something that looks more like this. X1 squared. I'll have a squared term for each of these things. And then we also will have cross terms, right? We'll have cross terms, x1, x2, x1 and x3. Something might be 0, so we could have an x2 and an x3. I'll put this in here, but just to remind us that it's there. Suppose it were 0. We'll see how we'll deal with that as well. X2 and x3. And what's our matrix? What should our matrix look like in this case? All right, so let's see what happens. As before, the x1, so we're thinking about this as being column x1, x2, x3, and then row x1, x2, x3. So if we put these together, this is x1, x1. Well, x1, x1 is, in this case, x1 squared, and so the constant, the coefficient out front, is 1. x2, x2 has to be 2, and x3, x3 has to be minus 3. Right, x1, x2, well, I get 2 of them, but I also have an x2, x1. So that 2 has to be split up into 2 different positions. Right, so these things together make this 2 that's up here. The 1 and the 1 that corresponds to x1, x2, and x1, x2. All right, so we have this minus 4 x1, x3. Well, that's right here. x1, x3, minus 4, but I also have x1, x3 down here, so I have to split that negative 4 up into 2 different pieces, get negative 2 and negative 2. And then finally, we might have a 0. We might have an empty cross term, but that we can make just with 0 and 0 as well. So we get a symmetric matrix out of it, just as before, and we can pull it off of this form of the quadratic form. So if I gave you this matrix to start, we could also go back the other direction. Suppose that this is our matrix A. What is Q at X? Well, Q at X, it has a negative 2, x1 squared. It has 0, x2 squared. And it has 1, x3 squared. Our cross term for x1, x2 has a 2 and a 2. So that makes 4, x1, x2. Our x1 and x3 is 0. And our x2 and x3 is negative 1. But I have 2 of those, which makes minus 2, x2, x3. All right. Good. Now, if the matrix A was a diagonal matrix, our life is a lot easier. Right, so suppose that I had the matrix 2, negative 1, 0, 0. It's a diagonal matrix. The quadratic form then will be 2x1 squared minus x2 squared. And there are no cross terms. Right, so no cross terms. So that's great, and we would prefer to have this. If this is a much simpler calculation, all those cross terms can get in the way and make our life a lot harder. So one thing that we're going to look at is to try to start with an arbitrary symmetric matrix and see if we can somehow adjust it to turn it into a diagonal matrix so that we get a quadratic form that has no cross terms. And so this is done through what's called a change of variables. So let's change variables. So we want to take x, let's start with just a 2 by 2 case, although it's the same in general. Let's take the vector x, x1, x2, and let's turn it into something. So by changing variables, what we mean is we're going to let x be py for some other unknown vector y, which we'll call y1, y2. So we've changed x, we've changed its coordinates by the matrix P. Now we're using these letters for our matrices in a very suggestive way. So remember that A was symmetric, which according to our, actually the last section, we can orthogonally diagonalize A. That is, we can write A as P, D, P inverse, which is P, D, P transpose, because P is orthogonal, which means that its column vectors are unit vectors which are mutually orthogonal, and D is diagonal. That's great because remember our goal is to take our quadratic form given by the matrix A and somehow or another turn it into a diagonal matrix. So if A is symmetric, we can get that diagonal matrix out of it by orthogonally diagonalizing the matrix. Right? So if X is Py, that means that y is P inverse x, which is fine. So now what are we looking at? We're looking at x transpose times A. So this is our quadratic form, Q at x transpose times A times x. But x transpose is then P times y transpose times A times x, because x is just Py, which means that now when I transpose a product, it's much like inverses. We can transpose each of the pieces, but then we have to flip the order as well. So this becomes y transpose times P transpose. So I've sort of distributed my transpose to each piece, but I have to flip the order that we see the pieces. Times A times x, but x is Py. Now what? Well, notice what we have. P transpose times A times P. Well, that's exactly what I get if I take this and I solve for D. If I take A is P, D, P transpose, that tells me that by multiplying by P inverse on the left, and by remember that this is P inverse is P transpose. So, and then by P on the right, because if I multiply by P, P transpose times P is the identity, because P transpose is P inverse, I'm going to get the matrix D back. But P inverse again is P transpose. So what we get is that D is P transpose AP. Which means I've managed to write my quadratic form in this form, y transpose dy, where D is a diagonal matrix, and that's great. That's nice because diagonal matrices are much easier to work with. Okay, so let's look at that with an actual example. Okay, suppose that this is my matrix, 5 minus 2 minus 2, 5, and we're looking at the quadratic form Q at x is equal to x transpose A x. All right, so here's our goal. Our goal is to find a change of variables. X is Py, for which Q at x is then y transpose dy, where D is diagonal. All right, that's our goal. Now And this is just another way of phrasing the question or the process: orthogonally diagonalize the symmetric matrix A. So in other words, all we need to do here is figure out what P and what D are. And by doing that, we've changed the quadratic form into one which comes with a diagonal matrix and therefore has no cross terms at all. So that's what we got to do. And I'm just going to tell you the information that comes from this matrix. The eigenvalues are 3 and 7, and we get eigenvectors corresponding to 3 and 7, 1 over root 2, 1 over root 2, and then minus 1 over root 2, positive 1 over root 2. This is just how it works out if we find the eigenvalues, we find the eigenvectors, and we normalize them. So now we've gotten through step 3 of our orthogonally diagonalize this matrix process. We found the eigenvalues, we found the corresponding eigenvectors, and we normalize them to unit vectors, which means that D is the matrix 3, 7. On diagonals, 0 elsewhere, and P is the matrix that comes from writing the eigenvectors in the same order. 1 over root 2, 1 over root 2, minus 1 over root 2, 1 over root 2. Okay, and so that's really all we have to do for this situation, right? So what that let's go a little bit further here. So 5 minus 2. So this was our matrix A. Okay, so here we've got D, here we've got P. So here's the idea, right? So remember, what is Q at X? Well, we should be able to read that off from here. This is 5x1 squared plus 5y x2 squared plus, so this was a minus 2, so that makes minus 4xy. So that's what we've got if we come up with the quadratic form corresponding to this matrix A. Now, what happens if I take x? Remember what we're trying to do here is we're trying to say that x is py. So we started with A, we found P, we found D. Let's just make sure we understand exactly what we found. Right, so here's my claim. So we can take this and we can think about the quadratic form that we get. This is 5x1 squared plus 5x2 squared minus 4x1, x2. Right, so that's the quadratic form that we get out of it. Here's my claim. My claim is that Q of any vector x, according to this quadratic form, is exactly the same as the diagonal matrix D. So Y transpose times D, which was our matrix here, times Y, but that we know what the quadratic form for that looks like. That's simple. That's 3y1 squared plus 7y2 squared. So my claim is that Q of x is exactly this if we let x equal py. That's our goal. We're going to let x equal py, and then we'll be able to get a simplified calculation. So let's just notice how that works. Okay. All right, so let's find Q at the vector minus 1, 3. Let's also find let's find it 2 ways. We'll actually plug it in right into here, and what do we get? We get 5 times x1 squared plus 5 times x2 squared minus 4 times x1, x2, which is 5 plus 45, which is 50, plus 12, which is 62. All right, and that's not so bad. And then these small dimensional cases, a 2 by 2 matrix, this is pretty easy to do. All right, so the power in this comes when you're working with larger matrices. Getting rid of cross terms makes life a lot easier, but we have to still look at it in this small dimension situation. So if x is py, well, that means that y is p inverse times x, but that's p transpose times x. And so P transpose, remember that P was 1 over root 2, 1 over root 2, minus 1 over root 2, 1 over root 2. So P transpose is going to be 1 over root 2, 1 over root 2. Now we're going across rather than down. Minus 1 over root 2, 1 over root 2, multiplied by x, which in this case was minus 1, 3. Which gets us minus 1 over root 2 plus 3 over root 2 for the first, and then the second makes 1 over root 2 plus 3 over root 2, which is 2 over root 2, 4 over root 2. So that's after we've changed our variables to y. This is y1, y2. All right. So now what happens if we take q applied to y1, y2, but with the diagonal matrix instead? So now if I take y transpose times the diagonal matrix D times y, what we end up getting is, according to our understanding, should be, remember our diagonal matrix was 3 and 7, so that's 3 y1 squared plus 7 y2 squared, which in this case gets us 3 times 2 over root 2 squared, which is 4 over 2, which is 2, plus 7 times 4 over root 2 squared, which is 16 over 2, which is 8, which gets us 56 plus 6, which is 62 as before. So we get the same thing either way. And again, it's not that much different in this low dimensional case, but if we had a higher dimension in our matrix, if it was a 10 by 10 or a 12 by 12, getting rid of the cross terms, that is turning it into a diagonal matrix, greatly simplifies the work that's actually required here. Okay, so let's look at some geometric interpretations. So some geometric interpretations of what we're looking at. Right, so suppose that I had, let's start with a diagonal case, and then we'll look at the more complicated cases. But suppose that I had q at x is equal to 3x squared plus 3x1 squared plus 5x2 squared. So that corresponds to the diagonal matrix 3, 0, 5, 0. All right, so this is x transpose d x for d equal to 3, 0, 0, 5. Right, that's what we're looking at. Suppose that I said find all x with q at x equal to 6. Right? So I'm looking for every vector which gets me a fixed output. So this corresponds to 3x1 squared plus 5x2 squared is 6, which is x1 squared over 2 plus 5x2 squared over 6 equals 1. Now, if I turn this into an x and y equation, this looks like x squared over 2 plus 5, 6xy plus 5, 6y equals 1. Now, y squared equals 1. So now if we're thinking about algebra, say a college algebra class, if I didn't have that 2 and that 5, 6, that would be like x squared plus y squared equals 1, which is the equation of a circle. So these constants that are out front, or in the denominator, serve to stretch what's going on in the x and the y direction. And what we actually get out of this in the x1, x2 axis is an ellipse. All right? So this quadratic form corresponds to an ellipse that's been stretched a bit in the x1 and the y and the x2 direction because of the constants that are out front instead. Now, if I had a quadratic form that had some pluses and minuses instead in it, suppose that if d were something like 1 minus 1, and so this corresponds to, and q at x is x transpose dx. This corresponds to q at x is equal to x1 squared minus x2 squared. If I would set this equal to a constant, instead of an ellipse, what we get is a hyperbola. Right? So if I looked at the equation, x squared minus y squared is equal to some constant c. Because of this minus rather than the plus, we don't get an ellipse, we get a hyperbola instead. So generally speaking, and this is true whether or not we had a diagonal matrix or not. So generally speaking, for any quadratic form, q at x, if I look at q at x equal to c for any symmetric matrix A, then the graph is one of a couple of options. It's an ellipse, it's a hyperbola, and it's two intersecting lines, or it's just a single point. So it's one of these things. All right, so the two intersecting lines comes from, really it's a degenerate hyperbola. This is what a hyperbola looks like. And if you stretch this all the way in, then we get two intersecting lines. And so that's how we can get that. We may end up just getting a single point corresponding to the origin here, but that's what we can possibly get when we look at q at x fixed at some particular constant for any quadratic form. Now the trouble is that sometimes what we've got is, rather than an ellipse that's just stretched along the x1 and x2 axes, we might have an ellipse that's been stretched in a funny way, stretched and rotated. Right? So stretched and rotated through, rather than the x1 and x2 axes, some different set of axes. And that happens when the matrix that we started with was not a diagonal matrix. So if we have a matrix that is not diagonal to start with, what that means is that our matrix A, right, so if we have A is P, D, P inverse, this means that we have this diagonal matrix in the middle, which gets us the ellipse or the hyperbola or the two lines or the point, but we've changed our variables on the outside, which serve to rotate or shift our entire axis system. So by changing our variables back to D, to the Y, by changing our variables back to Y corresponding to the diagonal matrix, what we've actually done is we've shifted this back so that, or you can think about this as just us turning our head, so that now this becomes the major and minor axes for our ellipse, and all of the calculations become a lot nicer. There's not really too much we can do to actually work with that. That's just a way of interpreting really what we're doing when we find the matrix P and D in this situation. And there's one last thing that we need from this section, which is called classifying quadratic forms. All right, there's a little bit of Calc 3 here. I'm not much, and in the end, when we get to actually answering the questions, you don't need the Calc 3 stuff. So if you haven't done Calc 3 yet, that's okay. But really what we're looking at, suppose that I had a function of two variables, f at xy is x squared plus y squared. We're thinking about this as our x1 squared plus y2 squared. Right, so this is our diagonal matrix 1, 1, 0, 0. Right, so this this would give us x1 squared plus x2 squared. And so that's what we're thinking here. The graph of this is actually a hyperboloid, right? So it's, a paraboloid. It's parabola that's been rotated around this z-axis. Right? So this is called, so when we have this, right? So when the graph is always above the xy axis. So when it's always above the xy axis, it might possibly touch 0. So when the graph is always greater than or equal to 0, or in fact, when it's bigger than 0 for xy not equal to 0, 0. So that's what we've got here, right? The value of this function is positive everywhere except for right at the origin, where the value of this function is 0. And when that's the case, when I have a graph of a function, so if I would take my quadratic form and graph it, think about it as a function of several variables and graph it. If I'm always positive except for right at the origin, we say that the quadratic form q at x is positive definite. Positive definite. All right, so if the graph, let me write this out in a bit more organized fashion. So if we have q at x, which is x transpose x, x transpose ax. Right, so if we've got this, if q at x is bigger than 0 for all x not equal to 0 as a vector, that corresponds to the origin when we're thinking geometrically speaking. So if we've got that, then we say that q at x, q is positive definite. And as it turns out, that's the case if and only if all of my eigenvalues are positive. Right? That's because that's the situation where our diagonal matrix corresponds to one with positive entries on the diagonal, which gets us a positive x1 squared plus positive x2 squared, which is why everything gets pushed up. Okay. If q at x is less than 0, below the xy plane, for all x not equal to 0, then we're going to say that it's negative definite. Q is negative definite. And again, this corresponds to all eigenvalues negative. Finally, it is possible that we have some positive eigenvalues and some negative eigenvalues, and in that situation, we say that the quadratic form is indefinite. So if q at x is bigger than 0 for some x, and q at x is less than 0 for some x. Right, so that is that the graph goes above the xy plane sometimes, but below the xy plane sometimes. Then we say that q is indefinite. And that occurs if and only if we have some positive and some negative eigenvalues. And so one example of this type of question, we might have a quadratic form q at x, which is, let's say, 2x1 squared plus 10x1 x2 plus 2x2 squared. And let's classify this, classify the form. So that is, decide whether it's positive definite, negative definite, or an indefinite form. Now you might be tempted to say it's positive definite because of all of the positive coefficients. But be careful. Remember, the positive definite means that it's positive for every single input. But this, if I had a negative x1 and a positive x2, this 10 here may overpower the positives that we get from the squaring. Right? Our x1 and x2 may be negative, which means this cross term might confuse the issue, and we have to be careful. Right? So what we really need to do is we still, in this case, need to orthogonally diagonalize the matrix that corresponds to this form. So this is the matrix with 2's on the diagonal, because that's our square terms. We have a cross term of 10, which means we have a 5 and a 5. So if I want to orthogonally diagonalize this matrix, I need to look for the eigenvalues and the eigenvectors. One of the eigenvalues will be -3, because if I say a minus 3 on the diagonal, that makes 5, 5, 5, 5. So that clearly works. The other one, what is the other? Is 7, because if I subtract 7 on the diagonals, I get -5, -5, and that'll be -1, -1, -5, 5, and then 5, -5. So we can see what happens with each of these. If lambda is -3, this corresponds to 5, 5, 5, 5, which row reduces to 1, 1, and then 0, which says that x1 is equal to -x2. x2 is free, so we get the vector -1, 1. I went through that quickly, but if you go through all of those details, this is what we would find. All right, for 7, this corresponds to the matrix -5, 5, 5, -5, which when we row reduce, we'll get -1, 1, which says that x1 is actually equal to x2, which gets us the vector 1, 1. So now I have an eigenvalue and an eigenvector for 2 different situations. The next step is, notice that they are already orthogonal. When I dot these, I get 0. Next, we need to normalize these, make these unit vectors. Although, in this case, actually, to answer this question, we don't even need to go any further. We can say right away that D is -3, 0, 0, 7. And since I see D, right, and D has a positive eigenvector and a negative eigenvector, according to what we wrote down before, this is indefinite. We don't need to go through the whole process. Right? If I just need to classify it as positive definite, negative definite, or indefinite, really all I care about are the eigenvalues. If they're both positive, it's positive definite. If they're both negative, it's negative definite. If they're mixed of signs, then it's an indefinite form. And that's what we've got here. And again, we can go back to the original form and verify. So we had 2x1 squared, 10x1 x2 plus 2x2 squared. So in particular, suppose that I put in 1, 1. So if I put in 1, 1, what am I going to get? Everything is positive. So this is bigger than 0. Right? But what if I put in q at -1, 1? And if I put in q at -1, 1, well then what I'm going to get is 2x1 squared, which is 2 times 1. I'm going to get -10, and then I'm going to get plus 2x2 squared, which is 2. So I end up with 4 minus 10, which is -6, which is less than 0. So I found an input which makes it positive, and I found an input which makes it negative, which means that it switches signs and it's an indefinite form. Okay, and that's all we really need to think about for this section. So at this point, you should be good. We've got one last section to go for the entire course, 7.4. We'll see you then.